Chapter 7.3 and 7.4 really talk about two things, anhydrides and then additionally acid and base strength. So begin with anhydride. Anhydride literally means without water. So that means if you have a metal oxide or a non-metal oxide, then what happens when we react them with water? Do they become an acid or do they become a base? So let's look at this first compound. We have sulfur trioxide, and so it is an oxide because it contains oxygen, but then it's a non-metal oxide because sulfur is combined with oxygen, and sulfur is a non-metal. So remember back to the periodic table, make sure you check, the difference between the metals and the non-metals. If it is a non-metal, then when it reacts with water, you're going to produce an acid. So this example, you have sulfur trioxide reacting with water to produce sulfuric acid. It's similarly going to happen whenever you've got like something like carbon dioxide, where CO2 is a carbon, which is a non-metal, plus oxygen, which makes it an oxide. When it reacts with water, you're going to create acid rain, so carbonic acid. And so it's the same thing. Anytime you have any kind of oxide that is oxygen with some non-metal, it's going to always react with water and produce an acid. And so this is why this is so important, because you have carbon dioxide, which is what we exhale. Whenever it reacts with water, our oceans, our air, our atmosphere, etc., an acid is going to be produced. And so this whole conversation of anhydrides, why it really matters is because it's all around us, and so we have to think about what's being produced and why. So non-metal oxides always turn into acids. But what about metal oxides? Metal oxides and oxides are the opposite. They always turn into basic compounds. So in this situation, you have lime, which is calcium oxide. Calcium is a metal. Oxygen is, once again, non-metal, but it's an oxide. When it reacts with water, it's going to form calcium hydroxide. And notice calcium hydroxide has an OH group on it, so it is a base. So just kind of keep that in mind. If you're wanting to turn something into an oxide into a into a base, it's going to have a metal attached to it. If you want to turn an oxide into an acid, it needs a non-metal attached to it. And so don't worry too much about the nuances behind it, but just kind of keep that in mind as you're thinking about how you might reduce your acid rain, or how plants might be able to have more or less acidic soil. Yeah, kind of interesting stuff. Alright, so then it also talks a little bit about strong versus weak acid. And whenever I'm thinking about strong versus weak, there's kind of two components to it. It's how many ions are being released in water when you throw an atom into it. So let's say we throw a molecule of hydrochloric acid into water. Hydrochloric is a strong acid, which means the hydrogen and the chlorine will completely break apart like what you see on the left. And so notice all of these purple versus all of these red. These reds are supposed to be your hydrogens, and the purple is supposed to be your chlorines. Okay, or whatever other compound is attached to your strong. But if you notice, when you throw it into solution, they're no longer attached. They're broken apart. And that's what it means to be strong. It has nothing to do with concentration. Okay, it also has nothing to do with being burned. You can be burned just as easily from a strong acid as you can from a weak acid. Okay, all it has to do with was when you throw it into water, what's being produced. The strong acids are considered strong electrolytes. So when you drink your Gatorade, you're replenishing your electrolytes. All that means is there are a whole bunch of charged molecules inside of your drink. Strong acids do that. They produce a whole bunch of charged molecules. And so they carry a charge. They're completely dissociated. Whereas if you take a weak acid, so acetic acid is one example. If you throw acetic acid into solution, the hydrogens are supposed to pop off. But instead, not every hydrogen pops off. And so I've circled all the ones that are in the bound state. Throw acetic acid into solution, throw some other weak acid into solution, they're not all going to pop off like the weak acids do. Some of them stay together in a bound state. And so when you're looking at this is important because weak acids act completely different than strong acids. And it's all because of this, of weak acids, they don't dissociate fully. If you can just remember that definition, you'll be fine. So how do you tell the difference between a strong acid and a weak acid? Well, what I do is I memorize a chart like this. Alright, this is one example. There's lots and lots of charts that list, here is the example of strong acids, strong bases. But for our class, if it's on this list, it's strong. If it's not on this list, we're going to consider it weak. Okay, so I listed some common weak acids down there: acetic acid, hydrofluoric acid, hydrocyanic acid. I also listed some weak bases. And so when you're looking at this chart and you're trying to decide, is it strong or is it weak? If it's on this chart, it's strong. If it's not, it's weak. All right, with that, go read section 7.5.